15 of them. So let's go ahead and dive right into the statistics material. For those of you that may have any questions on test 4, as far as doing your corrections, what we will do next week is our last class. We'll do the statistics test. I'll just allow the whole class for that. I don't like to lecture in the first hour of class and then have that same material on a test. So what we'll do is we'll just take the test in the first hour. And then if you have any questions on corrections or anything like that, we will answer those questions during the second hour next week. Otherwise, after the test, you'll be free to go. Okay, so statistics. There are 2 types of statistics. There's descriptive statistics, and there's inferential statistics. Descriptive statistics is just that, trying to summarize and describe what's going on. Inferential statistics is taking that next step, using those statistics to try to predict and make decisions. So to predict and decide on what to do. That's a little bit more in depth. We're going to leave the inferential statistics to a full-blown statistics course. For our purposes here, we're going to talk about more descriptive statistics. Get a little bit of vocabulary in here. We won't have a lot of time for vocabulary, but we do need to talk about a population. A population is just the group that you want to learn about. Now, the group could be people. It could be items, could be prices, could be a group of anything. A lot of times they use the term set, the set of things you want to learn about. Sometimes it's very difficult to define the population. For example, if I were to ask students about their favorite color, the population I want to learn about is not the colors. What I want to learn about is the students. I want to know what the favorite color is a characteristic of the students. So what I'm trying to learn about is them. So that is my population. Now, oftentimes, we can't reach the whole population, so we take a sample. And a sample is just a smaller group selected from the population. And there are a lot of reasons to take samples. We're not going to get into all the details. Realistically, there's like an hour discussion on samples alone. But a lot of reasons to take samples. If you have a large population, let's say we wanted to learn about what percentage of the people in the state of Wisconsin have completed some sort of a college degree. Now, we've got to be very careful with how we define that. Would it be fair to include 15-year-olds in that population? No, they haven't finished high school yet. Unless they're, a genius, probably haven't finished a college degree. So we would probably want to, first of all, define that as all people above the age of 18 is our population. So people above the age of 18 in the state of Wisconsin would be our population. Do you think it's feasible to contact every person in the state of Wisconsin that's over the age of 18 and ask them? No, it's not. Too much time is the big one. Money is the second one. Those are usually the two big factors that go hand in hand. You know, time and money are closely related anyway. You can't possibly contact them. Also, many would refuse to respond, so you're not going to be able to actually get to them at all anyway. It's not possible to get information from all of them. The time frame, you know, in fact, some people that haven't finished a degree, by the time you get to the last person and ask them whether they have a degree, some of those that said no earlier may have already finished their degree now. So the population changes. You have to do it in a relatively small window of gathering the information, or it's not valid, because the first person asked may have changed by the time you got done. So that's the reason we take samples. There's a lot of other reasons to take samples. Like I said, we're not going to get into. We want those samples to be representative. For a sample to be representative, what that means is the sample is very similar to the population. We have something called parameters. A parameter describes the population. A statistic describes the sample. If we have a good representative sample, the statistics will equal the parameter. If we take a sample and 38% of the people in our sample have college degrees, well, hopefully that means that close to 38% of the people in the whole state, in the whole population, have college degrees. If those numbers are way different, then that was not a very representative sample. The problem is we don't know what the population parameter is, so once we take that statistic, we don't know whether we're close or not. So we will never know whether the sample is really representative or not. So rather than trying to measure the results, we make sure that the process is as good as we can. So to make sure a sample is representative, there's two considerations. Sample size. Bigger is usually better to a point. If I survey two people, one person says they have a college degree and one person says they don't, can I say that about 50% of adults in the state of Wisconsin have college degrees? No. Way too small of a sample. This next one's a lot more complicated and more difficult to pull off in real life. Random selection. What random selection means, and you won't be tested on this definition, but that just means is every member of the population has an equal chance of being in the sample. In reality, this is very tough to pull off. I mean, most surveys are either mail or phone. Mailed surveys have a huge problem because getting a response. Mailed surveys usually get about a 20 to 25% response rate. About 1 in 5 to 1 in 4 people actually return those surveys. So you get a terrible response. Phone surveys the same way. A lot of people won't answer them, even those that do. You're not necessarily representing the population because there are still some people that don't have phones. So there's no way that they could ever be part of the sample. So then it's not truly random if it's impossible for some part of the population to be in the sample. Yeah. Yeah, getting a true representative sample, true random sample is extremely difficult. It's almost impossible. You guys being in the medical fields, it's a little easier. In the medical fields, of course, you have tests being done for like drug testing and testing new procedures and stuff like that. Well, those are a lot easier to control because you're selecting volunteers, of course, Not necessarily random samples because they have to meet certain criteria, certain conditions. But things are a lot more controlled when it comes to medical research than it is to other sort of statistical gathering, that's for sure. Okay, so when we're exploring, when we're trying to learn about these things, we're asking a question. The answer to that question is what is referred to as a random variable. If I ask you what your favorite color is, your response, your favorite color is the random variable. So we have two main types of random variables. We have categorical variable puts you into a category. That answer puts you in a category. If you respond that your favorite color is red, you're put into the category of people that prefer red. Then there is numerical. Again, numerical variable means the answer to that question is a number. How many credits have you taken so far? You're going to answer a number. How tall are you? That's going to be a number. How many kids do you have? How many cars do you own? Those are all numbers. There are many different divisions of categorical and numerical variables. I'm going to do a division on the numerical just because it's very important. Because you hear these words all the time, discrete and continuous. And I've heard a lot of definitions of both of these through the years. The best one I've seen is discrete is counted. How many credits have you taken? You would count. Well, 1, 2, 3, 4, 5, 6. Those are discrete. You can't take half a credit. Or how many kids do you have? Well, you count your kids. You don't have half a child somewhere, right? Continuous is measured. How tall are you? Well, you have to take a measurement. Continuous is almost always rounded to a specific place value. It's almost impossible to get it exact because no matter how precisely you measure it, it's always possible to go to one more decimal place or a more precise unit. One of the definitions of continuous, one of the technical definitions, is no matter how close two measurements are, it's always possible to find one in between them. And as you think about height, no matter how close to the same height two people are, it's always possible, if you keep measuring more and more precise, to find a difference between them. You might get down to the millionth of an inch, but they're not ever exactly the same. So we're going to start out looking at organizing data. My handwriting is horrible today. I apologize for that. Organizing these responses from these random variables. And let's just say that we have a categorical variable. And our options are A, B, and C. Make up whatever you want to for a question that has 3 optional answers for it. Right? And let's just write down our responses we get. What do I have there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 21, 22, 23, 25. So there's 50 responses. Now, just looking at that list of responses, can you tell me what the most common response was? Okay, some say A, B. Well, I guess C just for fun, even it out. It depends on where you look. If the psychology of the human brain, the physiology and psychology of the human brain, most people can take in about 7 to 13 items at a time and things start to fuzz out. If I'm looking right here, if I turn my pen on, it really does look like A is the most common, doesn't it? What if I'm looking right here? Really looks like C is. How about here? B definitely looks the most common. So we need some way of organizing that. It's just not possible to look at a set of data, a set of responses, and see what's the most common. So one of the first ways we organize data is in a table. And it's usually called a frequency table. So I'm just going to list response and frequency here. And I'm going to list responses A, B, and C. So in my list, I'm going to count how many A's there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 responses of A. How about for B? 1, that won't stay there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 responses for B. How about C? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 for C. Would not have expected A and B to be that close, would you? I would have expected C to be closer than being 4 away. So this is a frequency table. Now there's only 3 different possibilities here. If I would have had like 12 options, looking at this frequency table and seeing which one is the most common would even be kind of difficult. So we go from a table to graphical representations. And we mentioned these graphs a little bit at the end of the last unit, where we have our bar graph where we can list A, B, and C. And of course, we have to number up to at least 18 here. So I'm going to go by 5s up to 20. A goes up to 18. B goes up to 18. C goes up to 14. So now from the bar graph, we can definitely very quickly pick out which one's the most, which one's the least, just by looking at the height of the bars. So the biggest advantage to the bar graph is that quick reference. Which one's the most common response? Which one's the least common response? Did they choose more of A or C? You can tell which bar is larger. But if I asked you how many responded that C was their preferred, well, I trace that over. It may be difficult to decide whether that's 14 or 13. You saw that on the one bar graph on our test. Was it 8, 9, or 10? It was right in there. Well, I accepted any of those Because on a graph, it's tough to get exact numbers. If you need to know the exact number, then it's best to go back to the table. That's the strength of the tables. A little slower, but you get the exact numbers out of them. So that is summarizing the data visually, graphically. What we want to look at, we want to spend most of our time on today is summarizing data numerically. To make sense of that, of how we summarize it numerically, we need to talk about data distributions. And of course, when I'm talking about data distributions, I am talking about numerical data. There are data distributions for the categorical data. That's basically just the frequency table we saw up above. Let's say we are going to do test scores. The simplest way to represent a distribution is something called a dot plot. A dot plot is just a number line with dots plotted on it. So let's say that on the test, we've got a high score of 100. We're going to complete our number line here. Let's say we had nobody scored below 40 on this particular test. So all the scores on this test were between 40 and 100. We're just going to plot those scores. So let's say we're looking through the tests. We had somebody scored a 72. We put a dot above 72. Someone scored an 81. We put a dot above 81. Someone scored a 64. We put a dot there. 93. And for every test score, we put a dot on here. Let's say we have a second student who scored 74. I put my second dot above that first dot. And as I fill in the dots for these test scores, if I have enough students, it starts to make a very discernible shape. And if we fill in, enough, like I said, we have to fill in enough dots to get it. If we only have like 20 or 30 dots, usually doesn't give us a very definite shape. But if we have enough pieces of data, we generally get a pretty discernible shape. And it usually, if we trace through the top dot on above each number, we will generally get a shape something like that. It's called a bell curve. The technical name for it is a normal distribution. It's called a normal distribution because in nature, that is the shape or the type of distribution that things normally take. The height of people, if you took 3,000 people, measured their height and plotted their height on a dot plot, you would get a bell curve like that, a normal distribution. Almost anything you can imagine in nature, if you take enough measurements and plot them, you'll get that bell curve. Well, that bell curve can be described in a couple of different ways. So I'm going to remove the dots and still have a number line here. So let's say for one class, their bell curve looks like this. Well, how would we describe that curve? Well, we would say the center of that curve appears to be at about 76, right? That's the highest point of the curve and the center of the curve. So if I have another class, I plot their test scores, and theirs looks like this. How would we describe that class? Now, the center of the curve looks to be at about 70. So you'd say the curve, the green curve, that class probably didn't do as well as the blue curve. But what if I have a third class here that I'm going to do in red? If I went to describe that, its center is also at 76. But is that distribution the same as the blue curve? No. How would I describe the difference? There's less spread. There it is. That's less spread out. So the two things that we use to describe this, the center of the distribution, and then how spread out it is. We would say that the red curve is less spread out, has less spread than the blue curve. So let's talk about numerically describing the center. We actually have a few different ways of describing the center. To do this, let's get a set of numbers here that we're going to use. I'm going to use some smaller numbers just to make life easier on me. Oh, let's just stick with those 5 for now. There's my set of numbers. One measure of center is the mean. The mean is something that most of us have probably been calculating since about 3rd or 4th grade, called the average. A little notation here. N is the number of items in the set. So for this set here, N equals what? 5, because there's 5 items in the set. This symbol here means sum or total. Add them up, right? So the mean, if it's the population, the symbol for mean is the Greek letter mu. If it's a sample, the symbol for mean is X with a bar over the top of it. Both of those mean the mean. The mean is equal to the sum of all the values. X stands for all the values, each value, divided by N. Let's get away from the technical jargon and look at how do we actually just do this. Well, what that means is add them up and divide by how many are there. There's 5 there. So 8 plus 13 is 21, plus 9 is 30, plus 6 is 36, plus 19 is 55. Divided by 5 gives us a mean of 11. So that is one measure of center. Any questions on the mean? It's one most of us have seen before. The second measure of center is something called the median. If you think about a highway, the median is where on the highway? In the middle. The median is the middle number. To do the median, we have to do a couple things. First thing is we have to put them in order. So for this set, that would be 6, 8, 9, 13, 19. Second thing we have to do is find the location or position of the median. To find the position of the median, it is 0.5 or 1/2 times n. So for this data set, that's 0.5 times what? 5. You got it. So we get 2.5. Since this number here is a decimal, we round up, which tells us the third number is the median. So 1, 2, 3, that is our median. 9 is the median of this set of data. What if this didn't come out to be a decimal? I mean, it came out to be a decimal because n is odd in this case. If n is even, the median will be between two numbers. What do I mean by that? Well, for example, let's say n equals 8. So the position will be found by 0.5 times 8, which is 4. That is, since that is a whole number, the median is between that location and the next location. It would be between the fourth and fifth numbers in the list. We'll do an example in a little bit of that. The final measure of, well, main measure of center, there's another one that we're going to look at. This little, not as mainstream. The third measure of center is called the mode. The mode is the item that occurs most often. In numerical data, the mode's okay, but the mode is most useful for categorical data. Think about it, in categorical data, if you're going favorite color, is it possible to find a mean response? No, because you're not responding numbers. But you can find a mode. The color that was chosen the most often would be the mode. So that's where the mode is really useful, as categorical data. This data set, by the way, would have no mode because there's no number that's repeated more than once. If you talk about the mode, there's a lot of different theories. And statistics is not an exact science. Statistics, there's different theories, different schools of thought out there. Some people say there's either one number that's the most often or there isn't a mode. And that's the way we're going to handle it in here, by the way. Others say you can have up to 2 modes. Maybe there's 2 numbers that both appear 8 times in the set or whatever. You can have up to 2 modes. Some go so far as to make some fancy formula of it's the square root of n, whatever. You can have up to that many modes. We're not going to get that fancy. For our class, either there's one mode or there isn't a mode. When I do a test, I'll make sure I write it very carefully so that the mode is real clear. Yes. Yep. Yes, that would have to have 2 modes. Either if we allowed two modes, we would say A and B are both modes, or we would say there is no mode. There is nothing that occurs the most often. A little bit lesser known one that gets used in medical research is the mid-range. The mid-range is the average of the maximum and the minimum. The maximum is the largest number, the minimum is the smallest. So if I go up here, I put them in order for the median. 19 is my max, 6 is my min. So my mid-range would be 19 plus 6 divided by 2. When you do this, by the way, if you do this, or if you do the mean in your calculator, make sure that when you add them, you hit equals before you divide, or your calculator will mess it up. If you typed in 19 plus 6 divided by 2, it's going to tell us 22. That's not the mid-range. It's 19 plus 6, hit equals. Then divide by 2 should give us 12.5. There we go. So 12.5 would be the mid-range. How should these compare? The answer is, if I have a perfect, normally distributed set, here's my bell curve. Well, the mean should be right in the middle. The median should be the same number. The mode should be the same number. So if the data is perfectly normally distributed, those numbers, the mean, median, and mode should all be the same. The mid-range should actually also be the same. Most data is not perfectly distributed. One of the ways to test to see how closely it is to normally distributed is to find the mean, median, and mode and see if they're really close to being the same. Our data set we had up there, we had a mean of 11 and a mode of, or a median of 9. Those aren't real close. That's probably not real close to normally distributed. Most data is skewed. What skewed means is it's got one tail a little bit longer than the other. Like those two examples. This one over here is considered skewed left because the left tail is stretched out. This is considered skewed right. The right tail is stretched out. If I look at these data sets, the highest point on that curve should be the mode. Depending on how much it's skewed, the median will be slightly away from the mode in the direction of the skew. So the median, if it's skewed left, will be slightly to the left of the mode. If it's skewed right, slightly to the right. Now, to the left of the mode means it's a little bit smaller than the mode. To the right of the mode means it's a little bit larger than the mode. The mean is a little less predictable. If it's skewed left, the mean should be to the left, but it could be close or it could be really far away. So the mean will probably most likely be smaller, well, will be smaller than the median, definitely smaller than the mode. If it's skewed right, the mean will be stretched out to the right, larger than the mode and the median. This is one of the ways of testing these things, is finding the mean, and usually it's just the mean and the median and comparing them to see how they compare. So the question now is, which is the best measure of center? Well, I already said that the mid-range is not a mainstream one, so that's probably out. You've probably felt my opinion on the mode, where I said the mode really is only useful for categorical data. So that means that we are down to the mean and the median. If I take a poll, most people will usually respond the mean. Why? Well, because we've been working with it since we were really young. That's the first, I mean, we all learned how to average at some point in elementary school. And it just feels good. You're adding up numbers and then you're dividing, you're cranking out this mathematical formula, right? Feels satisfying. The median, all you're doing is arranging the numbers and finding the middle one. It feels kind of, first of all, it's kind of tedious to do, and it just doesn't feel that substantial. Let me give you an example. I don't remember now if it was 1983 or 1984. We're going to say 1983. University of Virginia advertised the average starting salary of a graduate in their 4-year marketing program. I say 4-year because I don't want to try to spell bachelor's. Their bachelor's degree marketing program was right around $78,000. Now, right now, $78,000 sounds like an incredible starting salary. Let's roll back to 1983, where in 1983, your average starting salary for a high school teacher was about $17,000 to $18,000. $78,000 a year is incredible. Well, what they failed to disclose here was that one of the graduates who actually did graduate with a bachelor's degree in marketing was a young man by the name of Ralph Sampson. Mr. Sampson was 7 feet 4 inches tall. Both his junior and senior year, Mr. Sampson was the NCAA Basketball Player of the Year. He was drafted #1 by the Houston Rockets that year. Houston Rockets, for those of you that don't follow sports, is an NBA basketball team. How much do you think he got paid that year? Several $million, right? He had a multi-million-dollar contract as the first draft choice in the NBA draft. Do you know how many $20,000 marketing graduates it takes to average a multi-million-dollar contract out to $78,000? A lot. That $78,000 was a mean. The median for that group was about $28,000, which is still not bad. Mr. Sampson, by the way, was the only one that made over, there was one other person that made over 35,000. So he was only one of, and that person made in the low 40s. So he was the only one that made over like $42,000, $43,000 in that group. He was the only one that made over 78,000 for sure. So do you think the 78,000 is a good measure of center? No. In statistics, we talk about stability. The median is more stable because one really large value isn't going to change the median amount a lot. Let's do an example here. Let's say I have the numbers 8, and I'm going to put them in order because I need them in order for the median anyway. Let's say I've got the numbers 8, 11, 13, 14, and 19. The mean, if I add those up, so I got 8 plus 11 is 19, plus 13 is 32, plus 14 is 46, plus 19 is 65. Divided by 5 is going to be a mean of 13. My median? Well, what's n here? 5. So 0.5 times 5 is 2.5, which tells us that median is in the third number. We round it up, right? So the median is 13. Well, what if I take that set of numbers, 8, 11, 13, 14, 19, and I add a sixth number to it, like, oh, let's see here. Let's do something that's going to work out well. Like 73. Now my mean, if I add those all up, that adds up to 138. And there's 6 of them now. 138 divided by 6 is 23. That's up from 13. What's my median? Well, what's n equal this time? 6. So it's 0.5 times 6, which is 3. Since that came out to be 3, remember when it's an integer or a whole number, that tells us it's between that spot, the third spot, and the next one, which would be the fourth spot. So it's between 13 and 14. We would find that by just doing, add them together, divide by 2, which is 13.5. Now, some of you are probably taught to do the median by just cross off the smallest. My pen will work. There we go. Cross off the smallest and the largest and work your way into the middle like that. That works on a small set of numbers. But if you have like 70 or 80 numbers up there, that takes a while. But you can see here, the mean went from 13 to 23. The median only went from 13 to 13.5. The median is more stable. And because of that, we usually view it as a better measure of center. Okay, it's 11:22, time for a break. Let's come back at 11:32 and we'll pick up from there. Okay, so the next step is to talk about spread. So the spread of our data, again, we're going to have a small data set that we're going to put up here, and I am going to put them in order this time. So we're just going to do 7, 10, 11, 13, and 18. Is that going to work out nicely? I'm going to do this. I'm going to change this to be 19, 13, and 19. Oh, change your 18 to a 19. Trust me, it'll be worth it in a little bit. Our first measure of spread is the range. The range is very similar to the mid-range. The mid-range, we added the max and the min, and we just averaged the max and the min. The range is just the maximum minus the minimum. So our maximum is 19 minus our minimum of 7 gives us a range of 12. Now the problem is I can find a lot of sets of numbers that have a range of 12. For example, maybe I'll do a second set down here that might be 7, 8, 11, 15, 19. That also has a range of 12. Would you say it's the same amount spread out as the set in black? Well, if you look at it though, if we did a dot plot, let's do 5, 10, 15, 20 here. So the set with the black numbers, we've got 7, 10, 11, 13, a little space for the 13, 13, and 19. In brown, we've got 7, 8, 11, 15, and 19. Looking at them that way, the brown looks to be a little bit more spread out, doesn't it? But they have the same range. They both have a range of 12. So range is a quick measure of spread, but not a great measure of spread. We tend to use something called the standard deviation. Along with the standard deviation, we're going to talk about variance as well. The two go together. They're not the same thing. They go together. They're just the result at different steps in the same process. There is a formula for standard deviation, but it is extremely ugly. I'm going to show it to you, but you don't even have to write it down if you don't want to. Symbol for standard deviation, by the way, is the Greek letter small sigma, like that, if it's the population. Or if it's a sample, it's just a small s. The formula I'm going to give you is if it is a sample. We're not going to show you the formula for the population. It is actually slightly different if it's a population. So the standard deviation is the square root of, remember what that symbol means? Sum, right? Add them up. X is each individual value minus, what's X bar mean? The mean. That's the mean. So we're going to subtract the mean from each number, square that difference, add them up, divide by n minus 1, and then square root it. That's the formula. Now, don't worry, we're going to give you a better way of doing it than using the formula. There is a step-by-step process that comes right out of the formula. Step 1, find the mean. That's what this here part of the formula is, finding the mean. So we're going to add them up. 7 plus 10 plus 11 plus 13 plus 19. That is 60 divided by 5, which is 12 is our mean. Somebody double check me. Just because at this point in the week, I don't trust my internal calculator anymore. Yep, okay, good. Step 2 is to subtract the mean from each number. What's that mean? Well, you got 7, 10, 11, 13, 19. We are going to subtract that mean of 12 from each of them. What is 7 minus 12? Negative 5. What is 10 minus 12? Negative 2. 11 minus 12. Negative 1. 13 minus 12. Positive 1 and 19 minus 12. 7. If we wanted to double check ourselves here, we would add that up. That should add up to be 0. These numbers here are called the deviations. That's how far each number is away from the mean. Called the deviations, or sometimes called the deviation from the mean. Brings us to step 3. Square each deviation. So negative 5 squared is, now if you're working on your calculator, remember, this is where you have to put parentheses around a negative number to square it. Otherwise, your calculator is going to try to tell you negative 25, which is wrong. Negative 5 squared is negative 5 times negative 5, should be a positive 25. Negative 2 squared is 4. Negative 1 squared, 1. Positive 1 squared is also 1. 7 squared, 49. Yeah. These are referred to as the real creative name, the squared deviations, because they're the deviations squared. Step 4. Find the sum. So I literally add those up. I get 80. You're going to love this name. This is referred to as, real creative here, the sum of the squared deviations. Aren't those math folk creative in how they name stuff? Step 5. This is the step that's a little bit tricky. Divide by n minus 1. What is n in this set? How many numbers are in it? 5. So n equals 5. Therefore, n minus 1 equals 4. Therefore, we divide by 4. 80 divided by 4 is 20. 20 is referred to as the variance. At the end of step 5, we have calculated the variance. Step 6 will actually give us the standard deviation, which is what we've been trying to find. Step 6 is square root. Square root of 20 is 4.47. That's the standard deviation. Yes, it is 6 steps. Yes, it is long, but it's better than trying to figure out that formula, I think. So let's compare that to that other set, 7, 8, 11, 15, 19. Let's calculate the standard deviation of this other set and see if that gives us a larger, we said that looked more spread out. Let's see if that gives us a larger standard deviation. Do you guys think you can follow those 6 steps on your own, or do you want me to work through it with you? Do it together? How about you guys? I'm going to give you like a 1-minute head start, and then I'll start through it. No, you don't want to do that? Okay, fine. You talked me into it. We'll just go. You tell me what to do, though. The step 1 is what? Find the mean. One comes before 2, yes. What's our mean come out to be? Seven plus 8 plus 11 plus 15 plus 19 should be 60. Divided by 5. I'm going to have you guys double check me. Make sure that's right. Okay. 12 works for me. What would, yes, it is. It's 12 again. What would step 2 be? Subtract the mean from each. So we have 7, 8, 11, 15, 19. And we shall subtract our mean. What is 7 minus 12? Negative 5. What is 8 minus 12? Negative 4. What is 11 minus 12? Negative 1. How about 15 minus 12? 3. How about 19 minus 12? 7. If I add these up, what should I get? 0. Remember what those are called? Deviations. Very good. Step 3 is to square them. Square each deviation. Negative 5 squared. 25. Good. Do you want me to wait a second, catch up? Okay. Okay. Negative 4 squared is 16. Negative 1 squared is 1. 3 squared, 9. And 7 squared, 49. Those are called, by the way, what? Those are the square deviations. Good. What's step 4? Add them up, the sum. If I add those up, I've got what? 100. She cheated. She looked ahead. Number 5. Divide by n minus 1. And yes, since n is 5, there's 5 numbers in the list, right? N is the number of numbers in the list. So we're going to divide by 4. It's always n minus 1. So 25 is the variance. I'm just feeling the love flowing today. What is step 6? Square root of the variance, which is 5. That is the standard deviation. Yeah, the variance is the 25 from the last step. So 5 is definitely larger than the 4.47 we had. So this does tell us that this set is more spread out. The standard deviation is a very good measure of spread. That is like the standard in statistics is standard deviation. What's that? Yes, but what the standard deviation is really good for if we know the mean and the standard deviation of something, we have a really good idea how it's distributed. I'm actually going to grab the book to see what percents. Every book uses different percents. Every book, I should say, rounds their percents differently here. It's the same percents, just... Okay, where are we? Let's go 350, it looks like. There we go. So the percents that this book uses. Remember, the center of this curve is the mean. Mean, median, or mode, we're using the mean. Because if the data is approximately normal, the mean and the median should be the same number anyway. If I go out 1 standard deviation on each side, so this is -1 standard deviation, this is +1 standard deviation. Now we're going to put numbers in for those in a little bit that might make it a little more clear as to what that means. 68.3% of the data is within 1 standard deviation of the mean. If I go out another standard deviation in each direction, so this is -2 standard deviations, this is +2 standard deviations. (95.5%) of the data is in that range. If I go out a third standard deviation, almost all, or 99.7% of the data is in that range. This is how the book breaks it down. I'm going to simplify it for you a little bit. Come on now. These curves are not real easy to draw and try to get straight. So this is the mean. -1 standard deviation, -2 standard deviations, -3 standard deviations. +1, +2, and +3. I'll give you a second to catch up on drawing if you need me to. I actually have to draw it. My curves are really crooked too. Up here we said 68% was within 1 standard deviation of the mean. Well, this curve is symmetrical, which means that's split evenly. Half of 68 is 34.15%. So 34.15% of the data in any normally distributed set of data is between the mean and 1 standard deviation on either side. What that gives us then is between 1 and 2 standard deviations is 13.6% on either side. Which gives us from 2 to 3 on either side is 2.1% of the data. And then outside of 3 standard deviations is 0.15% on either end. These percents are the same for all bell curves. On the skewed ones change. It has to be normal. It has to be normal, symmetrical. But most sets of data are close enough to be approximated with the bell curve. The percents are the same. Now, like I said, different textbooks round them differently. Like some of them, they just put 34 here and 13.5 here just to make them simpler. What's that? And those are the ones I have memorized. That's why I had to look these up to see exactly which ones this book uses. Because this book uses a set of numbers. My business math book uses a slightly different rounded set. And my statistics book uses the actual rounded ones that I have memorized. So, but what do these numbers mean? Let's say you want to buy a house. You want to buy a 3-bedroom, 2-bathroom house. And you do your research. And you look at the area you are moving to, that you're looking in, over the last several years, and we're going to assume that there have been no major changes in the market, like no rises in crime rates or interest rate drops or anything like that, big foreclosures or whatever. We're going to assume that over the last several years, you looked up the price of all 3-bedroom, 2-bathroom houses that have sold in that area. And you found that there is a mean of $120,000 with a standard deviation of $30,000. So we can label this now. The mean here is 120,000. I'm just going to put 120 there. What number is going to go here? right here. 90,000. We subtract the standard deviation of 30. 120 minus 30 is 90,000. What's going to go over here? 60,000. Perfect. How about here? 30,000. We're subtracting the standard deviation at each step. What's that? That $30,000 house? It depends on whether you're somebody who's going to fix it up and flip it. That might be the one you want. You're friends with the rats? Well, they know you're not going to eat them. Yeah. So anyway, going the other direction, what number goes here? 150. 120 plus 30,000. What goes here? I can't get it to 180. There we go. And then the last one, 210. Well, so let's say you're looking at houses and you find one, you just really love this house. And it's priced at $180,000. And your real estate agent is just pushing you like, you better put in an offer on this house because if you don't do it now, it's going to be gone. You better do it now. What's that? They always say that. Yep. What this table tells you is this. 180,000 is right here. If I add up those percents there, I get 97.75%. What is that telling me? Well, these prices here represent all the houses that are cheaper than $180,000. So what that is telling you is 97.75%, almost 98% of the houses that were 3-bedroom and 2 bathrooms that sold in that area over the last few years were cheaper than $180,000. Do you think that means there's a good chance you might find a cheaper house that you still like? Yeah. Yeah. Definitely, I would hope, right? Let's look at another application of this. Let's say you apply for a job and they make you an offer. And the offer is $17.80 per hour. Is that a good job or a bad job? A good offer, a bad offer? Well, it might not be in this area. I know areas where, cost of living is greatly increased. That may not be a great wage. What's that? Sure. But you'd be upset if somebody came in starting and made the same. Is it? Sure. Let's say you look in the area, you look at of other starting wages in the area. The mean is $15.10. With a standard deviation of $2.70 per hour. So we have our bell curve here. And our percents are still the same. These percents, again, never change for a bell curve. What numbers are going to go down here? What number goes right here in the middle? 15.10, 1510. That's our mean. It's always going to be in the center. How do we figure out what number goes here? Yeah, we subtract the standard deviation from the mean. 1510 minus 270 is 1240. How do we get this next number? Subtract it again. That's 970. How about this one? Subtract it again would be $7. Yeah. Going the other way, first of all, any questions on where those numbers came from? I started at the mean and I just subtracted the standard deviation at each step. This number now on this side is found by taking the mean and adding the standard deviation. So that will be 1780. This one will be 2050, and this one will be 2320, right? Just adding that 270 at each step. Your offer was 1780 right there, which tells you if you add up all these percents that you are making more than 84.15% of other people starting in that area. Or you could add up these percents, which would come out to be 15.85%. Only 15.85% of people in that area start out at a higher wage than that. So is that a good wage? Probably. That is something called the empirical rule. And like I said, those percents under the bell curve will not change. They might be rounded a little bit differently, but it's still the same percents. The weakness of that empirical rule, of course, is, well, what if you were offered $16 an hour? Well, that's somewhere in here. We can tell you're doing better than half, but you can't get a percent off of it. So for comparing other things that might be a little better, and it's usually used for comparing two different things, we can use something called a z-score. A z-score is found by taking a number, subtracting the mean from it, and then dividing that difference by the standard deviation. For the problem we just did up there, the number was 1780. The mean was 1510, so it's 1780 minus 1510 over the standard deviation was 270. So we subtract 1780 minus 1510 is 270. 270 divided by 270 is a 1, positive 1. That positive 1, the positive means that we're above the mean. 1 means that we're 1 standard deviation above the mean. If we look at the graph, that's exactly where we were, was 1 standard deviation above the mean. What the z-score is most useful for is comparing. Let's say you get 2 job offers. Job offer A for $18.10 an hour. Job offer B is for $16.50 per hour. Which one do you want to take? Let's say that they're in very different areas. Let's say that in the area that job offer A is from, the mean starting wage $14.80 with a standard deviation of $2. In the area from job offer B, the mean starting wage is $13 per hour with a standard deviation of $1.80. Let's find the z-score. Over here, the z-score, tell me, how would I calculate it? Perfect. It's the number that we're looking at, the 1810, minus the mean for that set, which is 1480, and divided by the standard deviation for that set, which is the $2. So if we subtract that, 1810 minus 1480 is $2.30, correct? No, $3.30. $3.30. We divide that by the 2, gives us 1.65. So that's positive, which tells us it's above or below the mean. Above, and it's 1.65 standard deviations above the mean. Not bad. Let's find the z-score for offer B here. What do I punch in? Perfect. 1650, which is the value, the number, minus 13, which is our mean. That's going to be divided by 180, which is our standard deviation. So 1650 divided by 13, or minus 13, is 350. Divided by 180, which is going to be 1.94. It's still positive, so it's still above the mean, and it's 1.94 standard deviations above the mean. So compared to other wages in that same area, offer B is a better offer, even though it's almost $2 an hour less. There might be other factors. There might be, schools and stuff like that that come in as well. Both of them are good offers. I mean, this is 1.65, this is 1.94. They're both above the mean, and they're, 1.5 to 2 standard deviations above the mean. Another example where this might get used is in quality control. Let's say you're the manager of a department store, and you have to get rid of an employee, a salesperson, and you've narrowed it down to 2 salespersons. You have Stacy and Alex. And you decide that whoever has the worst week next week, sales-wise, is the one out the door. So let's say Stacy has sales of $2,800 that week. Alex has sales of $1,900 that week. Does that mean bye-bye, Alex? No, she may have done better than Stacy, right? Let's say that Stacy works in electronics. Let's say we have found that the mean sales for all salespeople in electronics that week let's see here. It's $600. Oops, wrong. Let me go back on that. It's $4,450. Let's do that. With a standard deviation, I was thinking standard deviation and writing it down for me. Standard deviation of $600. Let's say Alex is in toys. Now, this time of year, toys might be pretty popular, but often it is not as good as electronics. So let's say that the mean sales for all salespeople in toys was $3,150. with a standard deviation of $500. What's that? Let's take a peek here now. Z-score for Stacy. How do I do it? Perfect. The sales, 2,800 minus mean of 4,450, and that'll be divided by 600. So we subtract, that is a negative 1,650. Is that correct? There's that negative, yeah. Divide that by 600 is negative 2.75. It's negative, which means they are below the mean. 2.75 standard deviations below the mean. Maybe not looking so good for Stacy. Let's look at Alex. What do we do to find Alex's Z-score? Same thing. Alex's sales of 1,900 minus the mean of 3,150 divided by standard deviation of 500. So 1,900 minus 3,150 is a negative 1,250 divided by 500 is a negative 2.5. That is only 2.5 standard deviations below the mean. They are both pretty poor, but Stacy's worse. Negative 2.7 is below negative 2.5. So I think Stacy's gone, and I think we're in a desperate search to replace Alex as soon as possible. Any questions? Now, obviously, this is just touching on the tools of statistics. There's so much more out there that you can do with them. That's where a formal statistics course goes in. In a 2-hour lecture, this is really all I can squeeze into it. There would be more vocabulary and processes I'd want to put in there in a formal statistics class. There are a whole bunch of pages here I'm going to write down. It is homework on statistics. Page 321, 1 through 7, the odds. Just looking at questions, general questions about statistics. 326 through 330. 1 through 10 is looking at graphs. 339 through 340. 1 through 9, the odd, is also looking at representations of data. The real meat of it comes here, 347 through 348. You got 1 through 9, the odd, that's looking at measures of central tendency, mean, median, mode. Page 353 through 354. 1 through 7, the odd, that is the range, standard deviation. Page 357, 358, 1 through 6 is talking a little bit about that bell curve. What do you think? That is all of our material for the semester. Next week, I will have the test out to the campuses so you can go in early to take it if you would like to. Because that is our last class, doing corrections is tough to do on that test. So when I write it, I usually try to write it easier. The average score on that test is usually right around like a 95 or 96. You can still do corrections if you would like to. Those of you here in Rice Lake, if you just stick around, I will try to grade them as you finish them up. At the other campuses, those are usually sent to me later in the day. I will try to have them graded before I leave here on Monday, because a lot of times they don't get here until I leave Friday afternoon. But you will have until, let's give you till noon on Thursday the 21st to do those corrections and get it back to me. So next week is our test. That's all we have next week. These homework should prepare you for that. You guys have a great weekend.